So because this water molecule's got a stronger difference in electronegativity from one end to the other, water molecules are going to be harder to melt or boil. So that's why water is a liquid at room temperature, whereas hydrogen sulfide, which has a much weaker difference in electronegativity between the two ends, is going to be a gas. It doesn't take nearly as much energy to break up those weaker attractive forces. Nonpolar molecules are held together by what are called London dispersion forces. London dispersion forces take place because of the motion of electrons throughout the molecule. Let's take, for example, one of these two shared electrons. Whee! It's being shared evenly between the two molecules. But freeze frame! For this instant, in that instant only, that side of the molecule is partially negative and the other side is partially positive. If it happens to come into contact with another nonpolar molecule that is just properly orientated, partially positive to partially negative, for that instant it can attract. A really weak attractive force due to the motion of electrons through the molecule, setting up temporary polarity, instantaneous polarity, because in the next instant these electrons are traveling near the speed of light, it's already back over to the other side. So these attractive forces are temporary, which makes them really weak. But the bigger the nonpolar molecule is, the more electrons there are, and the greater chance that there's going to be a stronger charge on one side or the other for an instant. So hydrogen has weaker attractive forces than methane. Methane, being a bigger molecule, is going to have stronger attractive forces. So these are called London dispersion forces, and they are extremely weak, which means it doesn't take much energy to break them apart. Melting and boiling point are going to be very low. Most nonpolar molecules are gases at room temperature, and only the really big ones, like the molecules that go into making oil and gasoline, those molecules can be liquid at room temperature. And most of these nonpolar molecules, if they form a solid, they tend to be really soft, waxy solids. Vapor pressure, very high. Because the attractive forces between nonpolar molecules are really weak, when they're a liquid, there's not much to prevent them from just breaking free and boiling off, or in this case, evaporating off. So because the molecules are very weakly attracted, the molecules can evaporate very easily. And of course, the more molecules that evaporate, the more pressure that they can exert on your container walls when they hit vapor-liquid equilibrium. Now, polar molecules can either be held together with dipole attractions or hydrogen bonds. And the only difference between them is dipole attraction is just the attraction of the partially positive end for the partially negative end. Okay? But in hydrogen bond attraction, something a little bit more incredible is going on. If you have two hydrogen sulfide molecules, sulfur is the partially negative end, so it's going to attract the hydrogen end of another hydrogen sulfide molecule. Right, they're going to be attracted together. However, in water, the electronegativity difference from one side to the other is going to be pretty high. It's 1.4. Now 1.7 is enough to be ionic. But in the case of water, because the difference in electronegativity from one side to the other is 1.4, that's nearly ionic. Alright? So not only do you have just attraction between positive and negative, partially positive and partially negative, you've got an almost ionic strength attraction between partially positive and partially negative. Water molecules stick together like nobody's business, which is why bugs can walk across the surface of water. There's surface tension there caused by the strong attraction of one end of the water molecule to the other end of another water molecule. This is why you can pour water into a cup and actually overfill it and have that little meniscus on the top. That's why water grabs onto glass to form a meniscus, grabs onto the side. This is why water is transported up a plant via its vascular system, because of hydrogen bonding. Water is incredibly sticky. Would you like to see how? Here's a piece of paper. There ain't much to recommend it there. But if we hit it with some distilled water, that's the power of hydrogen bonding. That's the power of hydrogen bonding. That's the power of water. Of course, water as a glue isn't really that effective. After all, water does evaporate, and when it evaporates, well, there's no glue left, and so it'll just fall. So polar molecules can either undergo a dipole attraction to each other or hydrogen bond attraction to each other. The difference is this. Dipole attractions have medium strength. Hydrogen bonds have high strength. Dipole attraction melting and boiling point tend to be pretty medium. Comparatively speaking, hydrogen bonds lead to high melting and boiling point for molecules. Vapor pressure, again, dipole attraction, medium. Hydrogen bonds, very, very low vapor pressure. Water evaporates, but it doesn't evaporate as quickly as, let's say, gasoline. Gasoline evaporates real quickly.
In these two containers, we have equal volumes of distilled water and acetone. I'm going to put them both onto the table at the same time to see how fast they evaporate. First thing, notice how the water clings to the desk. The desk is hydrophilic, which means it can attract water, whereas the acetone spreads out. That's because the desk is going to be but at the same time, notice that the acetone spreads out. The desk repels the water and yet does not repel the acetone. Let's let this sit here. As you can see, the acetone has evaporated away while leaving the water barely evaporated at all. Taking a look at reference table H tells us why. At room temperature, around 25 degrees Celsius, water has a vapor pressure of about 4 kilopascals, but propanone, which is what this nail polish remover is, acetone, has a vapor pressure that's a lot closer to, let's say, 31 kilopascals. That means that the propanone is going to evaporate at the same temperature a whole lot quicker than the water will.
So let's identify the type of attractive forces that there are between these molecules right here. Nonpolar molecule, that's London dispersion. Nonpolar molecule, London dispersion. Nonpolar molecule, London dispersion. Nonpolar molecule, London dispersion. Now let's see. This molecule here, Cl2 or H2, which one is going to have the stronger London dispersion forces? Well, hydrogen is the second smallest radius of any element on the periodic table. Helium slightly smaller. Chlorine's got 3 energy levels. Hydrogen only has 1. So chlorine's going to be a much bigger atom. Therefore, the chlorine is going to have the stronger London dispersion forces between its molecules than hydrogen does. Which is why on the periodic table, hydrogen has a melting point listed at 14 Kelvin, but chlorine has a melting point listed at 172 Kelvin. Stronger attractive forces leads to a higher boiling point. Okay, polar molecules. If it's got H on one side and NO or F on the other, this has H on one side and N on the other, it's hydrogen bond attraction, a strong dipole. H on one side, NO or F on the other, hydrogen bond attraction. H on one side, NO or F on the other, well this isn't NO or F, that's just straight dipole attraction. H on one side, NO or F on the other, well that doesn't have NO or F, it's sulfur, so that's just straight dipole attraction. H on one side, NO or F on the other, that's hydrogen bond attraction. So based on the electronegativity of a molecule, you can tell a lot of things about that particular molecule. And knowing the electronegativity difference between two atoms that you're bonding together, you can figure out what kind of bond you're going to form. Is it going to be a transfer of electrons, or are they going to be sharing electrons?